Qualitative analysis from October-November 23, variant 3.3. For each test, you should record all the observations in the space provided. Example of observations include color changes seen, the formation of any precipitates and its solubility in an excess of reagent added, the formation of any gas and its identification by a suitable test. You should record clearly at what stage in a test an observation is made. Where no change is observed, you should write no change. Where reagents are selected for use in a test, the name or correct formula of the element or compound must be given. If any solution is warmed, a boiling tube must be used. Rinse and reuse test tubes and boiling tubes where possible. No additional test should be attempted. So this is the introduction of every qualitative analysis question. Now the question begins from here. Fa9 contains one cation and one anion. The cation is one of the calcium, magnesium, manganese 2+, or zinc. The anion is oxide or carbonate. Part A. Describe reactions to identify Fa9. You are advised to test for the anion first. State any conditions needed for these reactions. Carry out your reactions and record all your observations. Deduce the formula of Fa9. So here, for 4 marks, they have asked you to give the formula of Fa9, means you have to find the cation and anion present in this Fa9. Now, in order to select the reagent to test the presence of cation, the qualitative analysis notes on the last page of paper 3 is like this. You have 2 reagents which can be used to deduce the identity of the cation present, and those 2 chemicals are sodium hydroxide and aqueous ammonia. So we can select these 2 reagents in order to confirm which cation is present. Now, if we want to test the presence of anion, which anion is present, they have said here the anion is oxide or carbonate. Now, in the qualitative analysis notes, only the presence of carbonate is tested. Like, you can add dilute acid and it will give off fizzing. That means carbon dioxide is liberated. That can be tested by passing it through lime water, which will turn milky white. So we will see if we add acid and fizzing is happening, it means carbonate is present, or else if it is not, then it must be oxide. So let's test the anion first. So for the anion, we will add acid in our given Fa9. So let's perform this test first. Now we will take a small spatula measure of Fa9 in a test tube, and I will add dilute acid here, which is hydrochloric acid in this case we have been given. But before we add hydrochloric acid, let me prepare a tube of lime water also, because if carbonate is present, the solution will give off carbon dioxide, which when passed through this lime water must turn this lime water milky. So now I will put a delivery tube through this lime water, and here is my delivery tube which I will pass through this lime water. And once I add acid in this carbonate, I will pass this carbon dioxide given off through this delivery tube into this lime water, which must turn milky white. So I will put both of these tubes in my one hand, and with the other hand I will add acid from here, so that as soon as I will add acid, I will put this rubber bung over the top and the gas given off must be transferred through this delivery tube into this lime water. So I will hold this tube here and I will add acid from this tube. So here is my acid and I will add through this tube. So you can see the gas is given off, which is transferred, and the lime water is changing its color gradually. It has not clearly changed the lime water milky because the carbon dioxide given off was a bit lesser, but it has shown us that fizzing was happening. It must be saying that carbonate is confirmed instead of oxide. So we will write this observation now. I have recorded this observation of fizzing that has turned lime water milky. It means carbonate is confirmed, not oxide. Now let us proceed to the next cation test. For that I have made a table here of two chemicals, aqueous sodium hydroxide and aqueous ammonia. Few drops first, followed by excess, because these two reagents are added in this way that few drops of these will form some color of precipitates, and then excess of the reagents will either dissolve those precipitates or will make those precipitates insoluble. So let's perform this test now. In order to test the cation, we need a solution of our given salt. But this is just, we have confirmed that is a carbonate salt. This is why in the paper they have asked you to carry out the anion test first, because once we try to dissolve this in water, the carbonates are not soluble. It means we need a solution and we do not have solubility of this carbonate in water. So how can I make a solution of FA9? I can take a small spatula of this FA9 and I can add acid, because in the previous part also I have seen that the carbonate was reacting with acid to give off carbon dioxide and a salt solution was produced. So I will take a small spatula in this test tube and I will add acid to make its solution. Now this is my FA9 solid and I will add hydrochloric acid here, and then fizzing will be observed, of course, but we have to make the solution, so we will wait for the fizzing to stop. So we will add hydrochloric acid here and we can see that the salt solution is prepared. Now we will use this salt solution to test the presence of cation. Now we will take 1 centimeter depth of this solution in a test tube and I will add gradually sodium hydroxide. Few drops first, followed by excess. So here is my sodium hydroxide and I will add sodium hydroxide using dropping pipette, and I will see the formation of precipitates in this. So let me show you here. If I add sodium hydroxide, white precipitates started forming, and if I add sodium hydroxide in excess, those white precipitates are dissolved. It means white precipitates dissolved in excess. So we will record this observation now. So I have recorded this observation. Let us proceed on to the next one, which is aqueous ammonia, in the same way. Now I will take 1 centimeter depth of this solution in a test tube and I will add aqueous ammonia. So here is my aqueous ammonia using a dropping pipette again. I will add this aqueous ammonia dropwise and we'll see for the precipitates forming or not. So here I can see if I added few drops, white precipitates started forming, and when I have added sodium aqueous ammonia in excess, those precipitates are dissolved. I will record this observation now. I have recorded all the observations here that white precipitates were soluble in excess, and I have also mentioned here that as FA9 was a solid, I have added HCl to make its solution, and then with few drops and excess sodium hydroxide and aqueous ammonia, white precipitates and were soluble in both excess. So let's look for the cation showing both these observations. Out of this table we have zinc 2+ saying white precipitate soluble in excess, white precipitate soluble in excess. It means out of all those they have given calcium, magnesium, manganese 2 and or zinc. We have zinc confirmed as in cation. Now if we look at the anion confirmation test, we have fizzing with acid. It means here we can say carbon dioxide liberates with dilute acid, so carbonate is confirmed. Therefore we can conclude that our FA9 is zinc carbonate. So I have recorded here the formula of zinc carbonate. Let's move on to the next part of this paper, where they say Fa10 is a solution of double salt. It contains 2 cations and 1 anion, all of which are listed in the qualitative analysis notes. Use 1 centimeter depth of this solution Fa10 in a test tube for test 1 to 3. So let's start test 1. Add an equal volume of Fa2, which is potassium iodide, and then there is a dotted line which suggests that in the same test tube we need to add aqueous starch Fa5. So let's perform this test now. Now I will take 1 centimeter depth of Fa10 in a test tube and I will add Fa2, which is potassium iodide solution, in equal volume. And when I have added equal volume of potassium iodide, I can see the color becomes a bit darker from the original color. You can see the color becomes a bit darker, and it suggests that if you have added potassium iodide and brown color is forming, it means iodine is formed. Now I will add Fa5, which is a starch solution, as they have said. With iodine, starch solution gives blue-black color. So here you can see blue-black color is formed. So I will record all these observations now. So I have recorded this observation here. Let's proceed with test 2 now. Test 2 says add barium chloride or barium nitrate, and then there is a dotted line. It means in the same test tube add hydrochloric acid or nitric acid. So if we look at the test for anions, this is one of the test for sulfate or sulfite. If you look at these two tests, sulfate or sulfite, firstly they add barium 2+, which could be barium chloride or barium nitrate, and we further add dilute acid so that those precipitates, white precipitates which are formed, are either insoluble or soluble, confirming the presence of sulfate or sulfite. So it means in this part they have tried to show you the anion present. So let's perform this test now. Let's take 1 centimeter depth of solution Fa10 in a test tube and add few drops of barium chloride to observe if white precipitates are forming or not. So we can see here, if I add few drops of white precipitates are formed, so sulfate or sulfite is present. Now if we add a strong acid to look whether these precipitates are soluble or not, we add hydrochloric acid, and if those white precipitates are not dissolving, it means sulfate is confirmed, sulfite is not present. So we will record this observation now. So we have recorded this observation. White precipitates formed and they were insoluble. It means sulfate is confirmed. Now let's proceed with the next test, which is test 3. Add aqueous silver nitrate, then add aqueous ammonia. Now if we look at the test for anion table here again, Ag plus means silver nitrate is added to test the presence of halide ions. It could be chloride, bromide or iodide. If white precipitates are formed, it means chloride. If off-white precipitates form, it means bromide, and if yellow precipitates form, it means iodide. So ideally they are here testing for the halide ion. So let's perform this test now. Now let's take 1 centimeter depth of Fa10 again in a test tube and add silver nitrate. Here is our silver nitrate. We will add using dropping pipette. Now we will see white precipitates are forming or any colored precipitates are forming or not. So let us add silver nitrate. There is no precipitates formed. Now let us add aqueous ammonia. Obviously there is no halide now, but now as soon as we add aqueous ammonia, we can see dark brown precipitates are formed, which are insoluble. So let's record this observation now. So I have recorded the observation for test 3, which says no halide ion is present. Now let's proceed on to the test 4, where it says, in a boiling tube, add aqueous sodium hydroxide to a 1 centimeter depth of solution of Fa10, and then there is a dotted line. So it suggests that in the same test tube, we need to add warm gently and carefully. Then again, there is a dotted line and they say remove from heat and add a piece of aluminum foil to the mixture. Now from here, they have ideally tested for 3 ions. Number 1, if you add sodium hydroxide, you can see with sodium hydroxide addition, you can test the presence of one of the cation. So if it forms any precipitates and those precipitates are soluble or insoluble in excess, it suggests you one of the cation. Then they have asked you to warm it in the second part, which says that if it gives off ammonia on warming, which can be tested by moist red litmus paper, it means the second cation, ammonium, is tested. And finally, they have said add aluminum foil. It means now, if we look at the nitrate or nitrite here, nitrate or nitrite, they are actually tested by sodium hydroxide again, but with aluminum foil. So here we have to again see the liberation of ammonia. In this way, in this part, test 4, they have ideally tested for the presence of 3 ions. Now let's perform this test one by one. Now we will take 1 centimeter depth of Fa10 in a test tube, and we will add few drops of sodium hydroxide first. So if we add few drops of sodium hydroxide, brown precipitates are formed, and if I add sodium hydroxide in excess, those brown precipitates are not dissolving. Now let us warm this, but once we warm this, we will put this in a test tube holder, and also we will put a moist red litmus paper over the top to see the presence of ammonium ion. So this is my litmus paper. I will damp it now using this water bottle. Now I will put this over the top of this test tube, and once I warm this, I will see the litmus color. Now today I have this Bunsen burner, and it is very easy to use. Sometimes there is no gas, so we can use this also. Now if I warm this on this Bunsen burner, a gas must be given off that will turn this damp red litmus paper blue if ammonium is present. It has started heating. Yes, it is gradually turning blue. So from the top you can see the exposed part of this litmus paper is clearly turning blue. It means ammonium ion is present. Now if we put aluminum foil and we check again the presence of nitrate, how can we check that again? I will take a damp red litmus paper, but with aluminum foil. So this time I will add a aluminum foil here. So this is my aluminum foil. This one is aluminum foil, and I will put this aluminum foil in this test tube, and now I will again test the gas given off. Okay, so I don't need to warm. I can see clearly this litmus paper has turned blue. So I will record all these observations now. So I have recorded these observations. Now let's proceed with the next part, where they say identify the 3 ions in Fa10 by writing the formula of each ion. In the question they have said solution is a double salt. It contains 2 cations and 1 anion. So from all the tests we have concluded that whenever we have added barium chloride followed by hydrochloric acid, we confirmed the sulfate. It means one of the anion is sulfate. Now the two cations are, if I look at sodium hydroxide test in test 4, red-brown precipitates which are insoluble in excess, we can see in the table of cation test, red-brown precipitates are formed which are insoluble in excess are of Fe3+. It means the cation 1 is Fe3+. Now when we have warmed this mixture of sodium hydroxide and our salt solution, a gas has given off which has turned damp red litmus paper blue, which shows that here in the second part ammonia gives off. So ammonia has turned this red litmus paper blue. It means ammonium ion is confirmed. So here we have all three ions detected as sulfate, iron 3 and ammonium. So let's record this here. So I have recorded here the formula of ions present in our salt. Now let's move on to the next part. In the next part, they have asked you identify the two tests in B1 that involve redox reaction. Justify your answer for one of the tests. Test numbers here and then justification for 2 marks. So now if we go back to the previous tests in B1, in the first part, they have asked you to add equal volume of Fa2, which is potassium iodide. So if I look at the oxidation number of iodine in iodide, it is I-1 iodide, right? So if I have added this Fa2 in Fa10 solution, the solution turned into a dark brown solution, which shows that this I- has formed I2 aqueous, because I2 aqueous is dark brown in color. So from here we can see the oxidation number of iodine was -1 and it has increased to 0, because in I2 elemental form iodine is 0 and every element in its elemental form has 0 oxidation number. So from -1 it has increased to 0. It means iodine was oxidized here. Now if we look at the reagent Fa10, we got to know that it has Fe3+ also. It means in the same part in test 1, when I have added potassium iodide, so iodine was oxidized, then what has happened to this Fe3+ in Fa10? If iodine was oxidized, then this must be reduced to Fe2+. Therefore, as an evidence of one of the tests, we can write here that iodine is oxidized and iron 3 was reduced. So the test 1 is redox. Now the second reaction, that is redox, is here when we have added aluminum foil in the last part. So aluminum foil means elemental aluminum has which oxidation number? That has 0. And if it is added to water and heated, the oxidation number of aluminum has changed and it only forms 3+. So this is again one of the evidence that test 4 is a redox. Therefore, these two tests, test 1 and test 4, must come here as a number. Test number 1 and test number 4 were redox. And if we want to write the explanation, what we can say here is, since I- is oxidized in test 1, or we can say, because we have to just write one justification, so it's enough, but as an extra, if you want to say Fe3 plus is reduced to Fe2 plus or something lesser than Fe3 plus. Now, let's move on to the next part where they say, give an ionic equation for the reaction of one of the ions in Fa10 with sodium hydroxide. Now, with sodium hydroxide, as I normally say in every lecture, whichever cation is present, like if Fe2 plus is present or Fe3 plus is present or copper 2 plus is present, whichever cation is present and you add sodium hydroxide, so the hydroxide ions are added. It means if you add hydroxide ions, the precipitates which are formed are of their respective hydroxides. So these are the precipitates. Now for Fe2 plus, these precipitates are green in color, green precipitates. Now if we have Fe3 plus, so the hydroxides, FeOH thrice, means they are red-brown in color. So red-brown precipitates. And if it is copper, then obviously copper 2 hydroxide is formed as a precipitate, which is blue, pale blue precipitates. So for any of the cation test, why sodium hydroxide, what ionic equation we can write here? So we can write here these ionic equations. So here you can write the ionic equation for Fa10, and Fa10 has this Fe3 plus. Therefore, with the state symbols, what you can write here is, you can say Fe3 plus, which was actually aqueous, when added to this 3 hydroxide minus, which was also aqueous, FeOH thrice solid, which means red-brown precipitates were formed. So here we comes to an end of 14 marks qualitative analysis question from November 23 variant 3.3.